Hello everybody, welcome back to another Gregorious Maths video. In this video, as promised, I'm going to be continuing on quickly with my classical homotopy theory series. And so, as with many fields of mathematics, of course, homotopy theory also uses category theoretical language. And so, in an effort not to assume too many preliminaries for this series, I will make the first video in the series, well, about the categorical preliminaries. So of course, if you know what categories are, what functors are, what natural transformations are, what adjoint functors are, which is basically the four topics I will be covering. And also, oh yeah, limits and colimits, then you can just skip this video, but if you're unfamiliar with any of those topics, then you know you can try and skip to the part roughly where that might be. So yeah, let's just get straight into this video. So, okay, so obviously the first thing I want to talk about is what a category is. And so maybe there'll be more, motivated, presentations of category theory, but obviously this series is not about category theory. It's just, I'm just going to be presenting you with a lot of definitions in this video and examples. So let's see. So first definition is obviously of a category. So a category C, and obviously these notes here will be posted in the description along with the extra blog post. So a category C consists of, and so we have some data in this category. So what is it? And technically we should be calling it a small category because I'm going to require that the objects of it form a set. But okay, we'll not get too bogged down into set theoretic issues here. So first of all, consists of, actually I don't, this is just a normal category, I don't assume that the objects are set, I'll just call it a collection of objects. Secondly, what must it consist of? Well, we have to have morphisms between objects, that is, arrows between objects. So, to any two objects, okay, so let's say, for any two objects, A and B, in this category C, we can associate to these two objects a new set Hom of A, B, which consists of arrows, consists of arrows F between A and B. Thirdly, this Hom set satisfies a few properties. So, third is that we can compose them. So we have a map, which will be denoted by a little circle called composition. And what it does is it takes in a map in Hom A, B, and it takes in a map in Hom B, C, and it outputs a map in Hom A, C. So what this looks like is we have a map A F from A to B, and then we have a map G from B to C. So these are the two maps F and G, and we have a map here which we'll call G composed with F, and this goes from A to C. What else do we have? We have fourth, and this is associative, so we'll write this as associative. So that is F composed with G composed H is equal to F composed G composed with H. So that's what that means. Fourthly, we have a special morphism which goes from A to A for any object A. So we'll write for all A in the objects of C, we have a morphism called the identity at A in Hom A, so that for any morphism f, so for any morphism f in Hom A B, what do we have? Well, we have that f composed with the identity at A is just equal to f is equal to the identity at B composed with f. So basically, composing with the identity doesn't do anything. And yeah, that's all of the data that we have. So let's just review this definition a little bit. So firstly, we have a category, and it consists of objects. So we have objects in the category, but also, so that's normal. You know, we could have a set, and that has objects in it too. But what's not normal is that we have morphisms. We have arrows between these two objects, and they have to satisfy certain properties such as composition laws, you know, identities, and so forth. Let's look at some examples. You know, these once we look at some examples, we'll realize that this is not some alien definition which was dreamt up by the utterly deranged. But you know, there are some very familiar examples. So let's see. What do we have? So the first one is the category of sets. And it's just denoted by set. Normally that's, you know, written in bold writing or a bold font, some kind of special font. And what does it consist of? Well, we have objects of set are just sets. And you know, we'll say small sets to avoid set theoretic issues or whatever. And we have that morphisms are regular functions. So, you know, we have normal functions as our morphisms in this set, in this category. Alright, what else do we have? We have the category of abelian groups, which is denoted by ab. So, and again, this is normally written in bold. So, what do we have in this? We have objects of ab are groups, abelian groups, my bad. Abelian groups. Again, we have another category group, which is denoted GRP group, which just is the same thing, except we have normal groups instead of just abelian groups. But okay. So the objects are abelian groups, and the morphisms are homomorphisms. Okay. What else do we have? So, okay, so we have, you know, rings, we have fields, you know, all of those things, they can all form categories in a similar way. But let's look at some more interesting, more topologically flavoured examples. And of course, the first one that comes into mind is top, which is just objects of top are topological spaces. And the morphisms are continuous functions. Okay, that's good. Now we have a similar category top star, where the objects are based spaces and the morphisms are base preserving functions. We also have S-man, which is the category of smooth manifolds, and you know, we have smooth manifolds and smooth maps. We'll just say smooth maps. Now, finally, I saved the best example for last, and I'll do it in a different colour. I'll do it in purple, and that is we have the category Homotopy. Yeah. We have Homotopy. And what this consists of is, well, we still have the objects being spaces, But now, the morphisms are homotopy classes of maps. So in this case, instead of hom xy being just continuous functions, we'll have now that hom of xy is equal to equivalence classes of maps. And similarly, if we put a star there, then objects will be base spaces, and these will be based homotopy classes of maps between x and y. So these are some nice examples. You know, we have, hopefully with the somewhat wide range of flavors presented here, you can see how they can come up in more algebraic settings, and also with the focus of this series, you know, they come up in more topological settings too. Okay, so there's some basic definitions and some basic examples. An interesting example, which I won't write out, but it's an interesting example actually, is you can define a group as a category with one object. So what I mean by this is, to any group, actually I'll write it out in very rough. So for any group G, we have a category BG. Now it only has one object, we'll call it star. And what it is, so hom between this object and itself is equal to the group itself, and then composition is the operation. So we require that every single morphism be invertible, that is, there exists an inverse, such that when you compose them we get the identity back. So the morphisms are the elements of the group, and the composition is the group operation. And we require it to be a groupoid, which means that every morphism is an isomorphism. But, you know, if we are relaxing it a little bit to monoids, then a monoid is literally just a category with one object. Not the definition I would give to a beginner, but an interesting perspective to just have in mind. Alright. Okay, so now we kind of move on slightly to making categories, new categories out of old ones. So this inspires the following definition. A couple of definitions, we'll say. First one, definition of an opposite category. So given a category C, we can form a category C op, which has the objects of C op are equal to the objects of C, and hom C op of AB is equal to hom in C of BA. Okay, and so what is C op? So it's got the exact same objects as C does, but the morphisms in C op are literally morphisms in C just reversed. So if we write, say for example, a morphism in C op is F op between A and B, this would just be F between B and A. Okay, so that's one way. And opposite categories kind of come up more naturally if you're defining, say, a contravariant functor, for example. But what else do we have? So, let's do it in a different color. Definition. Yeah, okay, so now we go on to subcategories. So, given categories C, we say that D is a subcategory category of C if so we have that the objects of D are a subset of the objects of C, and we also have that so if we have objects A and B in D, then Hom D of AB is a subset of Hom C of AB. Also remember that we still require, for this, we still need D to be a category, so we still do require that we have identities, we have composition, and we have that it's closed under composition too. We definitely want this category to be closed under composition. An interesting example of a subcategory is a full subcategory. And a full subcategory is when, well, we have this condition here, but this condition actually becomes, instead of we put a subset here, we just put an equal sign. So, for example, the category of abelian groups is a full subcategory of the category of groups, because, well, the objects of abelian groups are obviously a subset of the abelian set of all abelian groups is obviously a subset of the set of all groups. But then also, in both categories, as long homomorphism between two abelian groups, it's just the same thing. So, it's a full subcategory because these two Hom sets are equal to each other. Hopefully that makes a little bit of sense. And what else do we want to say? Oh yeah. Okay, so I also wanted to define what an isomorphism is in a category. So how strict are we with equalities basically in categories? For example, in group, let's say top, we want to look at spaces up to homeomorphisms. So, if we have a space which is homeomorphic to the n-sphere, in studying the n-sphere, we're also studying that space. So how is this piece of data, this equivalence, conveyed in a more categorical setting? So, definition. Given a category C, let's say C, with objects C and D in C, then F between C and D is an isomorphism if basically it's invertible. So if there exists some G between D and C such that F composed with G is equal to the identity on D, and G composed with F is equal to the identity on C. Okay, so that's just, so for example, in set, isomorphisms are really very loose. So in set, an isomorphism, two objects in set are said to be isomorphic if they have the same cardinality. So at that point we're literally just studying combinatorics. Also in top, as required, isomorphisms are homeomorphisms. In our category HOTOP, isomorphisms are homotopy equivalences. In group, isomorphisms are just group isomorphisms, so on and so on and so on. So this is a nice definition which conveys the equivalence that we would want in special cases. Alright. So next up we move on to the notion of a functor. Since this is kind of a little bit of a switch up, so to speak, in the topic, I will rub out the board now. And so while I'm rubbing the board out, I might as well talk a little bit about functors. When we have two categories, there are times when we want to study maps between the two categories, so to speak. So for example, in our homotopy theory series, we'll see that homotopy groups are a functor. What they do is they take in a topological space, so they take in an object in top, and they output us a group. So it's a functor between top and group. So, you know, these functors are important. Alright, so, what's the precise definition of a functor, you might ask yourself? That's a good question. Definition. Given two categories C and D, oh dearie me. Given two categories C and D, we say we say that F between C and D is a functor, and technically I'm just defining a covariant functor. We'll call it, say, what do I call it here? Oh, I just say it satisfies. Let's say if. So first of all, it has to map objects in C to objects in D. So, given some C in the objects of C, f of C is in the objects of D. But also, what does it do to morphisms? Given some f in Hom C A B, we have that f of f is in Hom D of f A f B. Thirdly, what does it do under composition, and what does it do under identities? So f of the identity at A is equal to the identity at f of A for all objects A in C. And fourthly, f of G composed with F is equal to f of G composed with f of F. And of course these are for morphisms in the appropriate category and, you know, between appropriate objects and so forth. We have a very, before I go on for any examples or whatever, we have a very related notion, which is that f between C and D is a contravariant. No, what I just described was a covariant functor. Contravariant functor if it's a functor between the opposite category is a functor. Is a covariant functor, but we'll just shorten it to functor. So, one of the differences, it will still map objects in C to objects in D, because obviously the objects of C op are the same thing as the objects of C. But the main difference is what it does to composition. Because, and so, firstly, for any f in C op, we have so C op of AB is equal to, okay, let me just write this out real quick. So if f is in C op of AB implies that f of f is, you know, in this of f of A, f of B, then what this means is, well, okay, that means that this is equal to hom C of B A. So that means that some morphism between B and A, we output a morphism between f of A and f of B. So the arrows get reversed, basically. Also, under composition, we get that f of G composed with f is equal to f of f composed with f of G. So that's a covariant functor for you. So it's just the same thing, but the arrows in the composition is all reversed and stuff. Alright, so, let's see, do I have anything else interesting written? Okay, so, now we move on to some examples of functors. So, okay, what examples are there? Firstly, we have some very important functors. Let's see, so example. We have some very important examples which forget structure. So for example, the functor f from ab to set, which literally just sends a group to its original set. It's forgetting the structure, forgetting the binary operation. So it's literally just called the forgetful functor. Similarly, we have a forgetful functor between top and set, so on and so forth. I won't go over any more really fascinating examples of functors, except for a functor between this group category, which we were kind of discussing earlier. It's just a homomorphism. So that's quite interesting because, well, this condition here, remember that the composition is the operation, so what it's saying is that f of x plus y is equal to f of x times f of y, so there we go. You know, I won't go over that anymore just because I feel like I'm kind of dragging on, although I will actually, saying that, I will go and say that pi n is a functor between top and group. So that's another interesting example. It's obviously going to be the main study of our series, so you know it's good to know that that is a functor. Actually, it's top star. I should say top star. We're being nice and technical here. Okay. Now, let's move swiftly on to natural transformations, because you know I don't want the first video straight off the bat to be like 2 hours, you know. So, although really that is all I have to say about functors anyway. So let's just talk about natural transformations for a second. Natural transformations are kind of like morphisms between the functors somehow. So, a good example of this, which we'll see in 4 videos' time, is the Hurwitz homomorphism. So, what's that? It's a morphism which takes in like it's a morphism between pi n, the functors pi n and hn, and it's we can go even further into it's a natural isomorphism, because it's a natural transformation. It's a nice morphism, but okay. So yeah, what they are functors between functors, or morphisms between functors, whatever you want to call them. And again, just because some, you know, very natural examples aren't immediately popping into my head, throughout the series you'll see that they are going to come up, basically. Alright, so what are they? So, definition. Given two functors f and g between C and D, we have that a natural transformation we'll call it phi between F and G consists of functors, or should I say morphisms? I should say morphisms, shouldn't I? Yeah. Of morphisms phi C for every object C in C, such that and now let's see what our diagram looks like. So say we have f of C. Now this obviously can go to via phi C to G of C, and also we can go down via f of F. So if some morphism f between C and D, f of F goes down to f of D, and then we have our morphism phi D to G of D, and we go down. And this commutes is the requirement for it to be a natural transformation. We can easily compose natural transformations by just composing these underlying morphisms here too. Do I have any interesting examples? Okay, so natural transformation is said to be a natural isomorphism if all of these phi C's are isomorphisms. Okay. And yeah, the Hurwitz map which I was talking about earlier. Okay. So now I feel like it's a good time to talk a little bit about equivalences of categories. So a functor, let's use a different color. Definition. A functor f between C and D is an equivalence of categories if there exists some G between D and C such that so that we have natural isomorphisms Fg isomorphic to the identity on D, and Gf isomorphic with the identity on C. So we have those two natural isomorphisms. So okay, let's take a pause here for a little second. Why are we using natural isomorphism and not just equivalence? Well, that's an excellent question. It's a natural question. And the reason is we don't really want strict equivalences because that would be too strict. Remember earlier when I was talking about how in categories we only want to care about stuff up to isomorphism. So for example, on top, we only care up to homeomorphism. If we required this to be an equal sign, what we'd really be requiring is that they have the same amount of objects. But we don't really care about that. We care about this. This condition here is slightly weaker, and it's asking for the same amount of isomorphism classes of objects instead. So that is, up to isomorphism, do you two have the same amount of objects? And that's why we restrict ourselves to natural isomorphism instead of straight up equal signs, because that would be a little bit too strict for what we want. Okay, good. So now, oh, of course, and a very important theorem about equivalences of categories is the following. Let's use the blue pen for this. I'm not going to go ahead and prove it, but, you know, it's an important theorem. So the following are equivalent. Okay, firstly, F is an equivalence of categories. And secondly, so equivalently, what we could be saying about F, or that is, it's an equivalent condition for it to be an equivalence of categories, is that F is fully faithful and essentially surjective. So the essentially surjective part means that every single object in D can be written as F of C, and yeah. Okay, so, and then the faithful, sorry, the, yeah, so a functor is faithful if, f of f, so basically, it's kind of like being injective, almost, so f of f equal to f of g implies that g is equal to f, that's faithful, and full is, that, we have a bijective map, so there is a bijection between Hom AB and Hom of f of A, f of B. So this is what it means for it to be full, this is what it means to be faithful, and obviously fully faithful is both. Okay. Good. So, okay, so that's all I really had to say about natural transformations. So, let's move on and swiftly move on to, let's move on to talking about adjoint functors. So, as I rub out the board, let me say a couple of words about adjoint functors. They're kind of like inverse functors. Obviously, it's a lot weaker than that. But if you have a functor going one way and another related functor going the other way, there's a likely chance that there'll be a joint in general. And adjointness is just a nice property for two functors to enjoy. Okay, let's see. So, and again, there are some important examples of adjoint functors in homotopy theory and in algebra. So let's see. Definition. Two functors f and g. So this notation here means that g is going from D to C and f is going from C to D, are adjoint. So they're adjoint if we have the following bijection, and that is that Hom D of f of x, y is in bijection with Hom C of x, g of y. Alright, so I don't intend for this section of the video to be long, so let's just go over a couple of examples. And so what exactly this means is that if we have a map, let's just use suspensions and loop spaces. Now, I'm not going to expect you to understand what a suspension or loop space is, but it's just that these symbols are a bit easier to comprehend. So, a map between the suspension of x and y would correspond to a map via whatever bijection this is, corresponds to a map between x and the loop space of y. So, okay, so that's what we're saying. Yeah. All right. Yeah. Okay. So, yeah. So that was my first example of the loop space. Suspension junction ultimately has an important consequence about homotopy groups, but also it's just a nice adjunction topology. Another one is the tensor homojunction. I think there's a whole Wikipedia page about that. So yeah, I don't really have anything else to say about adjunctions. So now we get on to the most, let's say, general part of this video, and that is colimits and limits. So let me just rub this definition out because, yeah, again, didn't really have much to say about those. Okay. Let me just take a sip of water. Refreshing. Yeah, colimits. So, first we'll define them, and then we'll see how colimits can generalize notions in fields of math that we might be familiar with. So, for example, direct products are colimits. Whatever. Yeah, we'll see when we get there. Okay. So first we require a couple of definitions first. The first definition is let J be an index category. So let's J be an index category, and let's just say and C be a category. Then a diagram of shape J is a functor x between C and J. Okay, so that's what a diagram of shape J is. Sorry, between J and C. Okay, so now we're going to be led nicely to the definition of a cone over X. So, definition, let's move swiftly on. Definition. So a cone over X with summit C consists of an object C, so this object here, in our original category here. So it consists of an object C and what else does it consist of? And a family of morphisms Ci between x of I and, sorry, between C and x of I, And just to clarify, this C is not the category but the object. This would be much more clear if I knew how to write mathcal, but on a board, but you know, whatever. Such that which diagram commutes? Well, such that for any morphism alpha between I and j, we have that, let's go from C, we'll go down to x of I via ci. Let's go down here via cj to x of j, and then let's go across here via x of alpha. So if this diagram commutes, then that's a cone. It's a cone over x with sum at c. Now, these are all some very general definitions and so forth, so on and so on. But we'll see the fruits of what good this is in a second. So stay with me. So let's see. So now we can define a limit. So basically, it's a universal cone. So definition, a limit of a diagram F from J to C is a cone. Sorry, yeah, is a cone over F which we'll denote by lim F C, such that it's universal in the sense that, yeah, any other cone let's say, what should we call our cone? What have I called it here? Yeah, we'll just call it C V. There's a unique map from C to, from the limit, yeah, it's from C to the limit of F, such that, and here's where the big diagram commuting comes in, and that is, so we're going to go from F of I, so we have our original cone, remember, so it's F of I, going, so we're going to go down via phi C. So this is our any other cone. So this is just some cone, and this is what it looks like. But then we have, so here we have another cone, which is our universal cone. So it looks like, what does it look like? It looks like this. Sorry. It's like this. And the unique property, the universal property, is that we have a unique map. Let's call it mu. Such that this diagram commutes. Okay, that's quite a long definition. So basically, all you need to take away from this definition is that limits are kind of cones that are universal in this sense that for any other cone we can kind of get ourselves into a commutative diagram situation. However, the main focus of this limit / co-limit situation will be co-limits. I'm getting a little bit tired and thirsty, so I'm just going to limit myself. I've got a bunch of examples written down here. I've got like 4 pages worth of examples and definitions and stuff. But I'll limit myself to just one example, and then I'll just say some closing remarks, and yeah, that'll be that. So, yeah, okay. And these are just the categorical preliminaries. So we can go through the process of defining cocones and cones and all that stuff. Sorry, cocones and that stuff by reversing the arrows. But let's just get straight to the commutative diagram. So basically, it'll be a commutative diagram that looks like this, and it's the same setup. Again, it's the same setup, it's just reversed arrows. We'll go this way. Yeah. Still go here, and we'll go up here. Okay, here we go. So this is basically just the commutative diagram which we get. So let me just pick out an example which I've written down. One that I like. Yeah, we'll discuss pullbacks then. All right, we'll discuss pullbacks. Because that's a nice fun thing, and you know, pullbacks describe many different concepts. Alright, so, and this is going to be co-limit, so there's a notion of a push-out too, but again, we won't be covering that. That's just the dual notion, so just reverse the arrows and, you know, try to figure out yourself what exactly that will look like. Here, pullbacks. Let's go. So, example. In a category C, a pullback is what is a pullback? A pullback is the co-limit of a diagram that looks like, well, what does it look like? Well, it's of the form, so we have some object, and we're going to another object, and we're going to another object like this. Yeah. Like this. So these are all just random objects. So the diagram looks like this. So let's take a look at, yeah, okay, so what it does, so really what it's consisting of is it's consisting of an object C in our category, along with two morphisms, along with two morphisms here and here, which satisfy the universal property. Let's just look at set for now. Alright, yeah, so let's say our category C is set. Then let's do it in red, because this is a nice important example and it nicely illustrates how co-limits can describe notions in other fields of math. So, alright, so what's a pullback? A pullback of a diagram which looks like, say we'll have A going via some F to C, and we'll have some G going to C via B. Consists of so the object which we were talking about before will be a subset of A cross B, and it's given by the set of all AB in A cross B, such that f of A is equal to G of B. And this object is denoted A cross with a little subscript C there, B. And it consists of projections which satisfy the universal property. Alright, let's look at how this can describe some notions in set theory. So, say for example, this object here is the singleton set. And also, I think I'm going to use it in the conflagration video, so the diagrammatic version of saying this is, we have A cross C, B, and we have the projections to A, we have a projection to B, and these maps are both going to C, via F and via G. And to denote that it's a pullback, we put this little weird symbol there to denote that. Okay, so yeah, so when C, alright, let's replace C with a bunch of different stuff. So let's put C equal to single set. So then we're going to have A cross star B going to A going to, and this is a unique F going to star, and this is a unique G going to star. And so because these two maps are both unique, they're both just the maps that send everything to that one point. Everything goes down to that one point. That means that every single object, that means that no matter which A you pick and no matter which B you pick, this condition is going to be satisfied. So therefore, the pullback A cross star C, so the pullback over just the singleton set is literally just this product here. Alright, that's nice. Now let's try it differently. Let's say that A is equal to the singleton set. Then what happens? What changes? So now we're going to have A cross C star. This is going to star, and this goes down to C, goes down to B, this goes down to G, this goes down via F. Now, okay, yeah, okay, so let's pick some C and C. So this map F, what it does is takes this point to just some arbitrary point C and C. So let's say that F of star is equal to just C. Then this set here becomes the set of all star B in this thing, such that C, this here becomes C, is of the form G of B. So what that is precisely is, let's see, okay, let's write this out. So it's the set of all star B equals B star cross B, such that F of star, so G of B is equal to C, and this is equal to the preimage of C under F. So that's just that's just a very interesting example, And yeah, so another example which I won't write out, but I had written down there, is that when both of these maps are inclusions, then this pullback becomes the intersection, and you can figure that out yourself. And yeah. Okay, so that's everything I had to say about categories. Maybe it's a little bit less, but okay, I didn't realise how long I'd be talking for. And yeah, so these are just the preliminaries. You can pick and choose what you want to watch, what you need to watch to be able to see the rest of the series. You might even want to just move on to number 3, higher homotopy groups, and then as soon as there's a categorical notion which is confusing you, you can just come back to this video. Again, the notes and the extra blog posts will be posted in the description, so feel free to read those. And yeah, thank you guys for watching, and I'll see you in the next video, I guess. Goodbye.